All right, so we have a little bit more about quadratics here. I guess they are kind of everywhere. Um, so as I mentioned before, when you solve a quadratic equation, there's some different options for what you can end up with in terms of the number and type of the solutions that you get. Now, these solutions are also called roots, and that's because of the graphing aspect, which we'll talk about more. So you can also be thinking about just, in our case, looking at the solutions to a quadratic equation. That's the same thing that's happening here. And basically it all has to do with the discriminant, which is, as you probably can tell from the quadratic that we did in the last video, is this is the inside of the square root. So if you think about it, for the quadratic equation, there is a part that is the square root of b squared minus 4ac. Now, the idea is if you have a positive number in there, you are going to end up with two solutions or two roots to your equation. So I'm going to put a little bit tight here, but I'll put that quadratic equation fully here just to kind of show you. So if you just look at the discriminant of a quadratic, you can actually get an idea of how many solutions it has, if that's something that's useful to you. And what you'll see is if this piece right here, this b squared minus 4ac, is a positive number, you're going to get negative b plus or minus some value all over 2a. That's going to be two solutions, plus or minus that root is two solutions, two roots. If that whole piece inside b squared minus 4ac is 0, this whole piece right here is gone. And all you're left with is negative b plus or minus nothing over 2a, so negative b over 2a. Without that plus or minus, that's just one solution or one root. If the inside of that is a negative b squared minus 4ac, well, you take the square root of a negative, you're not getting something real. You're getting an imaginary number. And so that's what it means to say two complex roots, is that those two roots are going to be imaginary instead of real numbers. Typically, graphically, what that means is you're going to have a quadratic that sits above the x-axis or below the x-axis. But the point is, it does not cross the x-axis. Two complex roots would be in that situation. One real root would be something like this. So notice it just kind of touches. And although I'm putting these all on the same thing here, just to show you, in the first situation, two different real roots, that would just be, as an example, something like this. So notice it all has to do with how many intercepts you have graphically. And we talk about more about that later. All right, so let's just take a look at this. We have an example. So it says, without solving, determine the nature of the root. So that just means, just tell me, does this have two different real roots? Does it have one real root? Does it have two complex roots? What's the situation? And we just use the discriminant. So you can identify your a, b, and c if you'd like. You can do b squared minus 4ac and see if you can determine which one it is, and then come back and take a look. So with a, we have 4, 20, 25. These are some big numbers here. But the discriminant b squared minus 4ac will have 20 squared minus 4 times 25. 20 squared is 400. And, you can do this multiplication in any order. 4 times 5 is 100. 100 times 4 is 400. We get 400 minus 400, and we get 0. So this is that case where when the discriminant equals 0, that tells us that there is one real root. And that's all we're being asked for here, is what's the nature of the roots. There's one real root or one real solution to this equation. And notice we do have one note here, which just says that if in fact b squared minus 4ac is a perfect square, meaning you do it and you get 16, or you get 25, or you get 36, then that means that the roots would be rational. So not just real, they would be rational. They could be written as a fraction. And that means that the equation could have been factored. So just note that these are all patterns that come up. The more you can recognize that stuff, the better off you're going to be. Okay, and the last bit of quadratics, ooh, so much quadratics here, is quadratics that don't necessarily look like quadratics. We actually saw one of these before in the factoring section. Now we have an equation. And the idea is just, if you can write it to make you think about a quadratic, then you can solve it like a quadratic. So it typically uses something called the substitution method, depending on how well you can kind of see the square. So this is always going to occur when you have an exponent here where the leading exponent is double the first one. So it is basically squared, is what I should say. So y squared squared is y to the fourth. So because of that, you can write this in a quadratic way. You can either just see it, or one thing that is common is to use a substitution. And if you want to do that, you would choose your thing to substitute as, like, I'll make it u. So I'm going to let u equal y squared, and I'll show you why. Because if I square both sides, y squared squared is y to the fourth. So the idea here is, now I can replace my y squared with u. I can replace my y to the fourth with u squared. So by writing it like this, what I want you to see is, now you have u squared minus u minus 20 equals 0. That is quadratic because it is squared. The highest degree is squared. But what it allows us to do is say, okay, well, now I have a trinomial that's quadratic. Can I factor it? And it would have to be u and u. And then we think about the factors of 20, 1 and 20, 2 and 10, 4 and 5. Oh, 4 and 5, because I need to have a middle term that is a 1. So I'm going to go 4 and 5. And then because the middle term is negative, I want the larger one to be negative and the smaller one to be positive. And then we're just using stuff we've already done. One of the most common math things that we do is trying to take a problem that is more complicated than we've seen before and make it into something we've seen before. So notice what I'm doing here is I'm taking something that's more complicated than a quadratic and I'm rewriting it as a quadratic so that I can solve it using things that I already know. So I have this, but then I'm not done because my solutions are not negative 4 and 5 because that's what u is equal to. So now we have to replace our u back with what u is equal to, and that's a y squared. So I'm going to replace u back with a y squared. So notice I'm just using this fact again. And then now I just solve each little thing I have here by taking the square root. So I'm going to get plus or minus the square root of negative 4. And I'm going to get plus or minus the square root of 5. Now, plus or minus square root of negative 4 is a plus or minus 2i. The square root of, we'll talk about this a little bit more, but in the next section, but negative 4, the square root of negative is an I. And so because the square root of 4 is 2, square root of negative 1 is I, we get plus or minus 2i. And then our other one, of course, as you can see, is just plus or minus square root of 5. So we actually have 4 solutions here for this. We have 2 that are complex, the 2i, and then we have 2 that are irrational, which is the plus or minus square root of 5. Okay, so for this other one, what we have here is solving another equation that can be written in quadratic form. But what you have to see is, if I were to let u, so now I'm still using the substitution here, x to the 1/3, and then I take and I square both sides, this takes you back to the idea of raising an exponent to an exponent. And you want to remember you need to multiply the exponent. So we're doing 1/3 times 2, which is just 2/3. So we get x to the 2/3. So I want you to see that because of that, we now have the same idea that we had before. We're taking something, we're making it into a quadratic. And it works because the term in the middle, if you were to square that term, you're going to get the first term. So notice now I can rewrite this as u squared minus 2u minus 24. So now I have something that can be written as a quadratic so that I can solve it and then go back and figure out my solutions. So this is just a handy tool to have for anything that doesn't look quadratic but can be written as a quadratic and then solved as a quadratic. So notice we have u and u, and we need two numbers multiplied together give you 24, but added give you a negative 24, but added give you a negative 2. So we have 1 and 24, 2 and 12, 3 and 8, 4 and 6. So you can probably guess that it's the 4 and the 6 that are going to end up making a 2. And because we want a negative in the middle term, that negative 2, we're going to go negative. We need opposite signs to get that minus 24 at the end. And then, as I said, I'll just skip the zero product property because I know we've seen it a few times now. And so this does tell me that I have u equaling 6 and negative 4. However, we also have to think about the fact that u is x to the 1/3 and x to the 1/3. And then in order to solve this for x, in order to have x by itself, we want to get rid of that 1/3. And you want to think about the fact that the opposite operation for raising to the 1/3 is to cube it. And that all just has to do with our exponent rules and the fact that when you multiply, when you raise something with a power to a power, you're going to multiply those powers. So notice that 1/3 times 3 is just 1. Oh, and I need to do that to both sides. I was getting excited about my colors there. Let's see. Okay. All right, so cubing both sides. Need to do that. Need to cube because we have equations there. And so that's going to give us x. And then 6 cubed is 216, I believe. Let me just double check. Yes, it is. And negative 4 times negative 4 times negative 4 is a negative 64. Okay, so here are two solutions to this. We've got 216 and a negative 64 solved by rewriting this in a quadratic way.